In this video, I want to talk about resonance. So this compound with this carbon anion can go through resonance, creating this structure. And the way it does that is essentially these electrons in this lone pair, this carbon anion, these electrons essentially fall down. And when they fall down, they form a double bond. So we see that here. But when they fall down forming that double bond, they push these pi electrons up on this oxygen, creating this oxygen anion. So now we've created this resonance structure. And then again, now we can go back where these electrons essentially fall back down, forming that double bond, and we see that here. And then they push these electrons back on this carbon, creating this structure. But why do we do this resonance in the first place? Because if we just had this structure and we didn't do resonance, we would have that formal charge of -1, all that electron density stuck and localized on this carbon. We would have all this negative charge stuck and localized on this carbon with that high electron density, negative charged electron density, all localized on this carbon, which we know is unfavorable. That's energetically unfavorable and that's not stable. However, if we can go through this resonance structure, creating this resonance structure, we can delocalize that negative charge. Instead of having that negative charge localized on the carbon, or instead of going through this resonance and having that negative charge localized on this oxygen with that high electron density, charge density, which is unstable, we can form these resonance structures, creating this hybrid compound. Creating this hybrid compound where now, instead of that negative charge localized on the carbon or localized on the oxygen, now it's localized between these three atoms. So now we delocalize that negative charge, and that's why we do resonance. We can take that negative charge and delocalize it and spread it out over a larger region, which we know is energetically favorable. When we do that, we have a lower charge density, negative charge density, which is energetically favorable. Because again, nature hates localized, squishing all that negative charge and localizing it over a small region with the high charge density. That's not stable. So that's why we do resonance. And again, something important to note is in reality, we're not going to have this compound or this compound. Really, it's going to form a hybrid structure between these two compounds that looks like this, with again that negative charge delocalized. However, something important to note is this actual structure that's actually made more closely resembles this compound rather than this compound. So why does this structure more closely resemble this compound? Because it wants that negative charge to be on that oxygen over carbon. Why? Because oxygen's more electronegative. Oxygen's more electronegative, so it can better deal with that negative charge. And we know carbon is not electronegative, so it hates that negative charge. So really, this resonance structure would have a little more electron density on this oxygen compared to this carbon, but again, it's still delocalized electron density, which is stable. And something else to keep in mind when you're looking at two resonance structures is thinking octets. In this example, every atom have octets, so neither one is favored due to that. However, if we had two resonance structures, maybe these two resonance structures versus this one, if we had these two resonance structures, we know this one would be favored. Why? Because all atoms have an octet. In this one, the atoms don't have an octet, so that's not favored. So therefore, they would have a resonance structure and a hybrid structure that most closely resembles this compound. And also, it will also do this because there are less charges. We know nature hates these localized charges, this localized negative charge, and this localized positive charge that's unstable. So that's another reason why this resonance structure is more favored. So now that we know these rules about resonance structures, what exactly is going on? What's exactly going on with these resonance structures? Well, really what's going on is we're rearranging the pi electrons. We're rearranging the pi electrons. So what do I mean? So again, we know resonance occurs between sp2 and sp atoms, never on an sp3 atom. But again, so essentially what's happening is, again, we know this carbon is sp2. Where we have this unhybridized p orbital that has both of these electrons. So this unhybridized p orbital has both of these electrons. We also know this carbon has a hydrogen bond and a hydrogen bond. So we know this carbon also has these sp2 hybridized orbitals, creating these covalent bonds, but I'm just focusing on the p orbitals. So again, this carbon has this unhybridized p orbital with 2 electrons in it. And then this carbon also has an unhybridized p orbital, but this p orbital has 1 electron in it. And this oxygen also has an unhybridized p orbital, but this unhybridized p orbital also has 1 electron in it. So this unhybridized p orbital has 2 electrons in it. This one has 1, and this one has 1. And again, so what's going on with this oxygen? It's also an sp2, so therefore we know it has 3 identical sp2 hybrid orbitals. This one has 2 electrons, this lone pair. This one has those 2 lone pair of electrons. And then this one has 1 electron, and then this carbon also has an sp2, so therefore we have this covalent bond. But this should be review. But again, so that's what's going on. We have these p orbitals. And essentially what's going on is with this resonance structure, this p orbital has 2 electrons in it, this p orbital has 1 electron, and this p orbital has 1 electron. And that's what's going on with this pi bond. This pi bond is the bond between these 2 electrons and these 2 p orbitals. And then this lone pair is just these 2 electrons in this p orbital. However, we know we can go through resonance. We can go through resonance creating this structure. So what's going on in this structure? In this structure, we also have these p orbitals. But we know when we have resonance structures, the p orbitals are being rearranged. So what's going on? In this resonance structure, we have 1 electron in this p orbital, we have 1 electron in this p orbital, and we have 2 electrons, let's say these 2 green electrons, in this p orbital. So what is going on? So essentially, when we do this resonance structure, remember what happens. Remember, these electrons fall down, forming a double bond. So we know these electrons, which are these electrons, fall down, forming a double bond. So essentially, these 2 electrons in this p orbital fall down, creating the electrons in this pi bond. So these 2 electrons turn into these 2 electrons, which again create this pi bond. Because again, remember, these 2 electrons, these lone pairs, fall down, forming a double bond. So therefore, these 2 electrons create the double bond. So therefore, these 2 electrons fall down, creating a double bond. So these 2 electrons are these 2 electrons. But again, when these electrons fall down, forming that double bond, then remember we push these pi electrons up on this oxygen. So what's going on there? These electrons fall down, forming that double bond, essentially pushing these pi electrons up on this oxygen. So what that means is, remember, these pi electrons were from this bond, from these 2 electrons and these 2 p orbitals. So when these electrons fall down, essentially what it does is it pushes these 2 p orbitals, these 2 electrons and these p orbitals, up onto this p orbital. So now these 2 electrons that were making this bond are now these 2 electrons. Because again, they fall down, creating a double bond, pushing these electrons up on the oxygen. And again, these electrons were these electrons, and again, they're pushed up on the oxygen, so these electrons turn into these electrons. So that's what's going on. That's what's going on with these resonance structures. We're just rearranging these pi electrons. That's all that's going on. And then the electrons can fall back down, reforming that double bond. So then when these 2 electrons in this p orbital fall down, these 2 electrons will form that double bond. So these 2 electrons would turn into these 2 electrons. And when they do that, then remember, when they do that, they push these electrons up onto this carbon. So these 2 electrons would go up onto this carbon. So these 2 electrons would be these 2 electrons in this p orbital. So that's what's going on with resonance. It's just rearranging pi electrons. So let's do another example. Let's say we have this compound. We know this can go through resonance, creating this compound. But again, why does this go through resonance? Remember, nature hates this localized negative charge. This high negative charge density localized in this region is energetically unfavorable. However, if we go through resonance, creating this structure, we create a hybrid structure that looks like this, with that negative charge delocalized over this entire region. So now instead of the negative charge being localized with a high charge density here, or a high localized negative charge density here, now that negative formal charge of -1 is now spread out. It's spread out throughout the entire atom with a low charge density, which we know is energetically favorable. Nature loves delocalizing charge. Whenever it has charge, it likes to delocalize it, spreading it over a larger region, and that's what resonance does. We can do that with resonance. So again, in terms of pi electrons, what's going on? Well, again, we know these are all sp2 hybridized atoms. So in this situation, this carbon with its unhybridized p orbital has 2 electrons in it. This carbon with its unhybridized p orbital has 1 electron. And this carbon with its unhybridized p orbital has 1 electron. And these 2 electrons create this bond, this pi bond. So this pi bond is due to these electrons. And then this carbon, again, it has one p orbital with these 2 electrons in it. And again, we see this carbon has a formal charge of -1. And again, if we counted all the electrons in this carbon for the formal charge, we would see an extra carbon, so that's why we have an extra electron, so that's why we have a formal charge of -1. However, we go through resonance, now creating this structure. So in this structure, now this p orbital has 2 electrons in it. And now this p orbital has 1 electron, and this p orbital has 1 electron, and that's why we have this double bond. So again, what's going on? Well, all that's going on are these 2 electrons essentially scooch down. So again, remember, these electrons scooch down, forming that double bond. So now we know these 2 electrons scooch down, creating that double bond. So these 2 electrons create a double bond. So these 2 electrons scooch down, so these 2 electrons turn into these 2 electrons, which create this double bond. So you can think of these 2 electrons as this double bond. So these 2 electrons scooch down, forming a double bond. But again, remember, when they scooch down, they push these pi electrons up on this carbon. So when they scooch down, they push these pi electrons up on this carbon. So therefore, they would push these pi electrons up on this carbon. They would push these pi electrons up on this carbon. So now these 2 pi electrons are these 2 pi electrons, creating this compound. So that's what's going on. And again, so pretty straightforward. The electrons fall down, forming that double bond. And again, so this double bond came from these 2 electrons. And then they push these electrons on this carbon. So now these 2 electrons are pushed on this carbon. So, and again, these electrons, which were these electrons, were pushed on this carbon. So these 2 electrons turn into these 2 electrons in this p orbital. So again, that's what's going on with resonance. So now just one last quick structure. Let's say we have this compound. So again, we know we can have resonance. These electrons fall down, forming a double bond, creating this structure. So again, why do we do this again? Because we don't want that localized positive charge, this high positive charge density on that carbon that's unstable. So if we do this resonance, we can delocalize that positive charge, so some of it's now on this nitrogen. So now we can delocalize that positive charge, essentially creating this hybrid structure. So instead of that positive charge localized on this carbon with a high positive charge density, or instead of it localized on this nitrogen with a high positive charge density, that positive charge has been delocalized, so now we have a lower positive charge density, which we know is stable and energetically favorable. But again, so what's going on? Well, again, we should know this by now. We have these 2 electrons, and we have these pi electrons. We have these p orbitals in this p orbital, and then we have these p orbitals in this p orbital. So originally, we had both of these pi electrons in this p orbital, and this p orbital was empty. But now with this resonance structure, now each of these p orbitals have 1 electron in them. So again, what happened? Again, remember, these electrons scooch down, forming that double bond. So we know these electrons form that double bond. So these electrons scooch down, forming that double bond. So these electrons create this double bond. So therefore, these electrons are now both of these electrons. So what's essentially this nitrogen is sharing these electrons in its p orbital. Instead of the nitrogen having both, now it scooches down. So now they each have 1 of them, forming this pi bond. And again, that's what's going on. And remember, in reality, we would have a hybrid structure. And we explained we would have a hybrid structure with that positive charge delocalized. However, with this hybrid structure more closely resemble this compound or this compound? Well, again, the number 1 rule is for all atoms to have an octet, and this does not follow that rule. This carbon does not have an octet. So this is not very favorable. So this is much more favorable. So therefore, this will much more closely resemble this one. Because again, this one doesn't have an octet. So really, in reality, we would see a compound that looks like this, a hybrid, but this hybrid would be a lot closer to this compound. So again, these are a couple examples of some resonance structures. And again, remember, the key point is the main reason why we do this resonance is to delocalize this charge, to delocalize these charges. Whenever we have charge, Whenever we have charge, maybe now we have this positive charge, we want to go through resonance, creating this structure. Because we can delocalize that positive charge, creating this hybrid structure. So now instead of the positive charge density localized here, or that positive charge density localized here, now we can spread it out. We can delocalize that positive charge over a larger region with a smaller charge density, which is energetically favorable and stable. And again, it's simply just rearranging these pi electrons. All resonance is rearrangement of pi electrons.